equals 1 minus gamma natural log of volume. Let's see. And I should actually look at the limits of integration here. So this is from some initial temperature to some final temperature, and this is from initial volume to some final volume. So we end up with the natural log of T final over T initial is equal to 1 minus gamma times the natural log of V final over V initial. So this is a relationship between final and initial temperature, final and initial volume, when you're dealing with an adiabatic process. E to both sides, we have this ratio of the final temperature over the initial temperature is equal to the ratio of the final volume to the initial volume raised to the 1 minus gamma. So for an adiabatic process, we have this relationship, perhaps a little bit more succinct. And so now potentially we have a way of relating temperature and the volumes. Well, I know that Vc over Vd raised to the 1 minus gamma is equal to the temperature at C over the temperature at D. I know that the volume at A and the volume at B raised to the 1 minus gamma is equal to the temperature at A over the temperature at B. But the temperature at A and the temperature at D are try that one again. A and B the temperature at A and B are the same because it's an isothermal process along there. And the temperature at D and C are the same. So in essence, these are equal to each other. So Vc over Vd is equal to Va over Vb. This whole term here is 1, and what we're left with is 1 minus the cold temperature over the hot temperature. Is the efficiency. Let's use some numbers. I have an engine. That is operating, make sure I get the language right. Yeah. Operating with a heat reservoir at 300 degrees Celsius. This engine is operating in the air. So, engine operating in air at 32 degrees Celsius. What is the efficiency of this engine? Well, assuming that it's working in the Carnot cycle, which hopefully was understood since I didn't state it, this is what we're looking right here. So the efficiency of the Carnot cycle in this particular situation is 1 minus the cold temperature, except you got to be using Kelvin. 32 plus 273.15 divided by the hot temperature, 300 plus 273.15. what do we end up with?
I used Celsius, but I got 89.33.
See, the trouble with Celsius is if you want 100% efficiency, you just have to work it at freezing level, and which nature, and if it's below freezing, you'll have over 100% efficiency.
I got 0.468.
So 46.8% efficient. The bigger temperature difference, the more efficient it's going to be. Because you have this great amount of energy, the source of energy that you can pull from, and you're dumping it into anything that's excess can be dumped into the environment that we assume is not heating up significantly for this one. We will deal with an environment that, sort of a middle ground environment that does heat up. It's like running a heater in a room. Questions? All right, let's take a break there. We're going to come back and do the auto cycle, OTTO, auto cycle, and then we will look at what was originally referred to as a challenge problem, and then we'll talk fluids and how physics textbooks are wrong, but we don't care. All right, so let's take a look at the Otto engine. So you have a cylinder with a piston sitting on top of it, or sitting in it. You inject a gas-water vapor mixture into this and basically press down. It's an adiabatic compression, so we're not having heat, there's no heat exchange yet. It's just we shoot something into it and we push down. Then we ignite it. The piston doesn't automatically move yet, but we ignite it. The isochoric is an isochoric, so the volume is staying the same and pressure builds. You now allow the piston to move and it's pushed up during the power stroke. There's no heat exchange at this point. It is adiabatic. And then you open up an exhaust vent, which causes depressurizing. And then you inject another set of gas vapor mixture into it, compressor stroke, and basically you're doing it over. You continually do it over and over again. Very, very similar to what happens in an actual car engine. Let's take a look at this from a PV diagram point of view. So we're starting out right before the compression stroke happens, so we're starting out with more volume. We go through an adiabatic compression. It should not dip down like that. Call that point A to point B. We ignite, but we hold the volume. So it's isochoric, volume stays the same. Up to point C. We have a power stroke, so our volume starts to expand again. And then, point D, and then we have an isochoric depressurizing, and we end up back where we started. Obviously, one thing that is not included in this diagram is time. From energy exchange, we have compression stroke, so we have work being done on the system. Work, I guess that's A and B, so work A, B. Then we ignite. Work is being done by the system. So now I will stick minus signs. And then we release whatever leftover energy we have. Into the air for the rest of us to breathe.
So this is a two-stroke engine.
Because in the four-stroke, maybe, I'm trying to remember what a four-stroke engine versus two-stroke engine is. I was thinking two-stroke engine is that 2 cylinders, and the four-stroke you get 4. But
I'm pretty sure the four-stroke is like, there's 2 extra strokes for, with no ignition. It's like,
is that to get rid of the exhaust?
removes exhaust, then brings in fresh air and fuel,
Oh,
and then
okay.
something like that.
Okay. Oh, make a note. And hopefully you have an answer for that by the next group. All right, we end up back where we started. What's the overall change in thermal energy?
0.
One would hope. We will assume it. So for the overall total thermal energy, which should be the change in thermal energy throughout the whole process there. I guess from A to A would be 0. In terms of the change in thermal energy as we go, we have work being done on the system over there, so we've got this work AB plus QH in the next set, and the next one minus WCD. So the system is losing energy by doing work. And then minus QC would be equal to 0. So we have WAB minus WCD is equal to plus Q hot minus Q cold is equal to 0. So we have Q hot minus Q cold is equal to WCE minus WAB. This is just manipulation. And what we end up with here is that this is the work being done by the engine. The negative of the work done on the engine. So let's take a gander at the efficiency. I know the efficiency is 1 minus QC over QH. Now, in the isochoric process, pressurizing and depressurizing, we have energy being put into the system without the volume changing. So what's going to get affected? If we don't heat into the system but keep the volume constant,
Pressure.
and think about it, if you have a pot of water and you put a lid on it and you put heat underneath it, yeah, pressure will build.
Temperature.
Yeah, temperature's gonna change. But how much will the temperature change? Well, we have a formula for it. And that marker does not work on it. very much related to the NC delta T that we did for, as we put energy into ice and then water. So for QC, this C right here representing sort of the cold. And unfortunately, I am using C as a state as well as C for cold. So in step 2, 1, 2, in this process right here, I've got N times the specific heat of whatever the gas is at a constant volume times Tc minus Tv. And in step 4, when I'm going from D to A in that process, QH is equal to NCV times, and then we'll just think through the signs. In this particular section right here, during this last bit, I'm venting off, in essence, hot gas. So I'm going to be losing energy. In other words, I have my QH is QC's backwards there. Yeah. This should be H. That should be C. QC should align to this part, and QH should align with this. Times, all right, so as we're venting heat, I would expect A to be colder than D is. So if I did TA minus TD, I'm going to get a negative number, which seems appropriate. Except for the fact that QC in this formula right here is positive, so I actually should reverse that. Yeah, I think in the future I'm gonna change the formula, probably put a plus sign there or something. All right, so the rationale is, the way the textbook is dealing with it is that this QC right here is a positive number. That they put absolute value marks around it. Because I know that TD is bigger than TA, if I want QC to be a positive number, it needs to be TD minus TA. That's the rationale. So this becomes 1 minus QC in big CV, TD minus TA, divided by QH, which is in CV, TC minus TB. We'll have to 1 minus temperature at D minus temperature at A over the temperature at C minus the temperature at B. Obviously, we're not done yet. Questions up to there before we bring in the adiabatic processes? Then let's bring in the adiabatic processes. I know that we've just derived it, but I know that final temperature over the initial temperature is equal to the final volume over the initial volume, raised to the 1 minus gamma, where gamma is the ratio of the heat capacity with constant pressure divided by the heat capacity with constant volume. So from this, TV over TA, because that's the adiabatic process there, so that's the process I'm working on. It's going to be equal to VB over VA to the 1 minus gamma. And I know that T, the other process, TD over TC, is equal to VD over VC to the 1 minus gamma. All right. The last bit that we need to engage here is that I know the volume at B and the volume at C are the same. The volume at A and the volume at D are the same. Again, that won't work this time. So the volume at B and C are the same, so this is the same as TC. And TA and TD are the same. Oh, wait, sorry, not temperature, wrong one. V is the same. So this is the same as, so B and C are the same, so this is VC, A and D, it's the same volume over VD to the 1 minus gamma is equal to TV over TA. And so now I have a relationship between the temperatures. So TA over TV equals, should be TC over TD. And so I have TD minus TA, I want to get stuff in terms of C and B. So 1 minus TD minus TA over TC minus TB